Welcome to the course Large Deviations. The main goal of the course is to make the basic overview of the main concepts of the theory. The course will include approximately 14 lectures, where we are going to discuss the basic results and ideas of this amazing theory. We start our discussion from rare events associated with the law of large numbers for independent random variables. After that, we consider some rare events associated with random vectors. And only then, building some intuition, we will be able to go to the definition of large deviations and basic classical results as contraction principle, Schilder's theorem, Gertner's-Ellis theorem, and others. The information about the course, lecture notes, homework exercises you can find on my webpage using the link below the video. This lecture we are going to start from some basic examples. So assume that you have random variables x1, x2, x3, and so on. They are independent. And also they take two values, 0 and 1, of I is equal to 0. And the probability that it is equal to 0 is equal to 1 over 2. And also it is equal the probability that xi is equal to 1. Okay, and it is 1 over 2. Then we are interested, what is the frequency of obtaining of heads? So we consider 1 over n of Sn, where Sn it is the sum of all random variables from 1 to n. Actually, it is x1 plus and so on plus xn divided by n. And from the probability theory, you know that this probability goes to 0. I'm sorry, not to 0, but goes to the probability, goes to the expectation of x1 that is equal to 1 over 2. And this convergence you can interpret as follows. Either you can consider the probability that the frequency deviates from 1 over 2 on the epsilon, it goes to 0. And then this property we call the weak law of large numbers. It is weak law of large numbers. Or you can prove, just working a little bit harder, you can prove that that 1 over n as n converge to 1 over 2 almost surely as n goes to infinity. And then we call that the strong law of large numbers. Law of large numbers. But in this course, we are going to interesting about so how fast the probabilities goes to 0. So actually, we want to consider, for instance, so that probability here. So it's here. And you see then when number n becomes larger and larger, the probability becomes smaller and smaller. And then the question is, okay, but how small it is? How does that probability depends on n? So do you have something like convergence like 1 over n, or probably you have some better convergence like with the speed e to the power minus n, and so on. Why this question can be interesting? So one of the reasons is that when you know additional information about these rare events which you consider, then you can say more about the properties of the, you can say more something about some additional properties of the model that you consider. So very simple example could be that if you can, for instance, say that this probability goes to 0 exponentially faster, then just having that property and using the Borel-Contelli lemma, you can get this convergence for free. So we assume that we have a family of independent random variables that we denote by x1, x2, sorry, x2, x3, and so on, and they are independent. And also, let's assume for simplicity, let's fix that, let's say that expectation is equal to mu. That is some number. And also assume that the random variables have the second moment, which implies that variance exists. It is sigma square. That assumes that it's larger than 0, and also assumes that all random variables are identically distributed. So they are independent and identically distributed. And then, as before, we define Sn that is the sum C1 plus and so on up to Cn. And we know that by the law of large numbers, for instance, weak law of large numbers, that this sum converge to mu in probability. Going back, it's exactly in this sense. Then we consider the probability, as I said, of 1 over n as n minus mu larger than or equal than epsilon. And you know by Chebyshev inequality that it is less or equal than that 1 over epsilon square variance of 1 over n as that is equal to 1 over epsilon square. And you know the properties of variances, for instance, that when you have that variance of constants multiplied by a random variable, it is constant square multiplied by a variance of random variable. I want to use that. It is 1 over n square, and then it is variance of Sn. And variance of the sum of independent random variables, it is sum of variances. We also use that here, and you will get epsilon square. And since all random variables x1, x2, and so on are identically distributed, also they have the same variance, which we denote by sigma square. You will get something like n sigma square, and then divided by n square. And of course, this goes to 0. And it is how we prove actually the weak law of large numbers. But you see that this probability here goes to 0 like 1 over n. And as we will see later, so this estimate is really very rough. You can get much better result than we obtain it with the Chebyshev inequality. We will be able later to get the exponential convergence to 0. And to demonstrate that, I would like to start from very simple example where we can do some precise computations, which allows us to somehow compute this or estimate this probability better than we did that by Chebyshev inequality. Let's consider the example. 1.1. And here we also assume as before that psi1, psi2, psi3, and so on are also as before IID, independent, identically distributed. But additionally, assume that mu is equal to 0 with And also assume that their variance is equal to sigma square is equal to 1. And moreover, let's take them normally distributed. Psi I has, each psi I has a normal distribution with parameters 0 and 1 in that case. Then you know that the sum of independent normal distributed random variables is again a normal distributed random variables with mean that is the sum of means and variance that is sum of variances. In particular, this implies that when you consider 1 square root n as n, and compute expectation and variance, you will get the expectation 0, variance 1, and as we said, the sum gives me also the normal distribution. Actually, it will be the normally distributed random variable. And then let's consider the probability 1 over n as n, but here let's write like that. Let me go back and say that in this case, we consider it was the expectation here, and we had the mu plus epsilon, we had mu minus epsilon, and we asked what is the probability that this random variable here belongs to one of that infinite intervals. But now for simplicity of computations, sorry, I want to consider only like only one side. That is here. And also let's assume that that x is equal that x is larger than 0. Once again, maybe picture. So expectation mu, it is 0 now. And then we took x here. Oops. And we ask what is the probability that the frequency, that the mean value, like 1 over n as n belongs to that interval. Then let's do the standard computations. It is a probability 1 over n as n larger or equal than x. And then let's multiply the left and right hand sides by square root n. Here you will get square root n as n larger or equal than x multiplied by square root n. And then this random variable is normally distributed with parameters 0 and 1. Therefore, you can precisely compute that expectation via the density. You will get 2p integral from x square root n plus infinity. Then you have the density of e minus square divided by 2 dy. And then we can use the property that the tails of that the integral that we have is equivalent to 1 over square root 2 pi x. Here, oops, I'm sorry. Let me. Before I will write that, let me write that actually precisely the property that I want to use, and it is like it is exercise size. When you consider the integral from x to plus infinity, e minus y squared divided by 2 dy, it is equivalent to 1 square root 1 over x e to the power minus x squared divided by 2 when x goes to plus infinity. And here we understand when we write that fx is equivalent to g of x, it means that f of x divided g of x goes to 1 when x goes to in this case. Oh, therefore, you see that just using this formula, we can continue. And to continue, let me copy that part here. We will make now it smaller. And it gets me 1 square root 2 pi. And after that, you have 1 over x. And in my case, it is 1 over x square root n. And then you have e to the power minus, and then this point to the square. It is x square n divided by 2. And now in this case, as n goes to infinity, because when n goes to infinity, then x square root n also goes to infinity. And I'm sorry, it is not exactly equal. It is equivalent. And you see that for the normally distributed random variables, this object converge like e to the power minus something that goes to infinity. And we would like to be also more precise. We actually want to focus on this exponent here, how exponentially fast it goes to infinity. We would like to capture this constant here. And to do that, what you can do, you can kill this exponent by the logarithm and then see what happens. Therefore, we can write the following. We can write the limit n goes to infinity, and then we can take logarithm of the probability 1 over n as n larger or equal than x. And you see, when you will do like that, then you should obtain so the exponent will be killed, and you will see that, but still here is a parameter n, which goes to infinity when n goes to infinity. Therefore, you also want to kill it. And you can write 1 over n of logarithm of that probability. And when you will write this, you will see that this limit is the same as the logarithm. And here it is 1 over square root 2 pi, 1x square root n. And then you have e to the power minus x squared n divided by 2. And just using the properties of logarithms, you will see the logarithm of that part divided by n, and logarithm of that part goes to minus infinity. But then you divide this, but this constant it goes here to 0, and you know that the linear function is faster than logarithm. Therefore, this with of multiply by logarithm of that will give you 0. Then after that, you will have a logarithm of the exponent, and the logarithm of the exponent. So then logarithm and exponent disappear. You have this term, and then divided by n. So that n and that n will be killed. And you see that the limit is minus x squared divided by 2. So it is what we obtained for normally distributed random variables in the case when x is larger than 0. When you are interested by this interval. You can also consider the case when x is smaller than 0. yeah, x larger than 0. And then ask about the probability that this random variable is in this interval, but then using the symmetricity of normal distribution, you can trivially come to the conclusion that the limit of when n goes to infinity, 1 over n logarithm the probability of 1 over n Sn less or equal at x is equal to minus x squared also divided by 2, but also x for smaller than 0. And let me probably repeat this. Just copy, just to put these equalities together for x positive and x negative, and our answer is like that for every x. I'm sorry, that is for x negative, and for x positive, you obtain the same. It is if psi1, psi2, and so on are independent, and with normally distributed with parameters 0 and 1. So you see that probabilities itself, these probabilities, they go exponentially fast to 0, and even we can catch that precise constant here, and that constant is equal to minus x squared divided by 2. And then the natural question, okay, now we consider another random variables. Can we get the same result? Do we obtain also minus x squared divided by 2, or we obtain something else, which is specific to the distribution of random variables that we consider? The next section, it is coin tossing. Here, assume that we have random variables are independent, also identically distributed, or shortly IID, random variables. Such that they take two values, 0 and 1, with probability 1 over 2. Xi is equal to 0 is the probability that xi is equal to 1 and is equal to 1 over 2. And we, as before, define Sn, it is the sum. And we are interested in the question, what is the limit when n goes to infinity, 1 over n logarithm the probability of 1 over n Sn larger or equal than x. But you remember the picture from the previous time that we considered mu, and then we made like small step to the right or to the left. Here actually is mu, and for this case, mu is the expectation of x, say 1, and it is 1 over 2. Actually, this point here, it is 1 over 2. And then we want to consider also two cases. One case, it's here, it's x. And later we also consider when x is smaller than 1 over 2. Actually, this probability, this means that random variables 1 over n Sn is in that red interval. Good. Then we consider this, and our question is, what is that? Can we get something like minus and then I of x? And is this I of x, for instance, x squared divided by 2, as it was in the previous case? Or probably it is something different. I just want to say that in this case, that will not be 1 x squared divided by 2, it will be something different. And we want to precisely catch that. Let's start here x larger than 1 over 2. Even you can take larger or equal. Okay, then let's start some computations. We first consider the first case. We assume that x is larger than 1. That is a case where you can compute something very precisely. And in this case, limit n goes to infinity. 1 over n logarithm the probability 1 over n Sn is larger or equal than x. It is. Let's note that Sn, it is the sum of random variables that takes two values, 0 and 1, and you sum them, you sum n random variables. Therefore, the sum cannot be larger than n. And you also divide by n. This implies that 1 over n Sn cannot be larger than 1. But now you choose x that is larger than 1. Oh, therefore, this event here, it is the empty event. And therefore, the probability of empty event is equal to 0. And logarithm of 0, we assume that it is equal to minus infinity. Therefore, here immediately you will get minus infinity. Then assume that x is from 1 over 2, comma 1. By the way, this assumption about that logarithm of minus infinity is equal to the logarithm of 0 is equal to minus infinity. It is just convenient assumptions which will allow us just write this kind of expression here without caring whether the probability is equal to 0 or it is not equal to 0. Then the case x is between 1 over 2 and 1. And here we will start the computation. We compute or try to estimate the probability that this probability that is equal to the probability that Sn is larger or equal than Xn. But Sn takes values 0, 1, 2, 3 up to n. Therefore, you can sum over all values, all possible values of Sn that is larger or equal than x multiplied by n. It is here k larger or equal than xn, and you have the probability Sn is equal to k. And Sn, it is the sum of independent identically distributed Bernoulli random variables. And you know from probability theory that the distribution of the sum is the binomial distribution. Therefore, we know precisely what that probability is. And that probability, it is it is 1 over 2n, then the sum k larger or equal than xn, and then you have binomial coefficients nk, where nk, it is n factorial divided by k factorial and minus k factorial. And now our goal will be somehow estimate the sum which we obtained here, or estimate this probability to find the corresponding limit. And to do that, let's note then from below the sum can be estimated by the maximal element which you have here. It's trivial. Therefore, you will have x to n, and then you have maximum of k larger or equal than xn of nk. And from the right-hand side, each element in the sum you can estimate by the maximal element that you have in the sum. The total number of elements in the sum is n plus 1. Therefore, you will obtain n plus 1. Probably this looks like a rough estimate, but for us, it is enough. And then it is maximum nk. Then after that, let's note that when you write the binomial coefficients, like for fixed n, like n0, n1, and so on, and then up to nn, then you will see the following, that first coefficients start to increase up to the average, and after. But here, we take the maximum, we consider the maximum of binomial coefficients starting from x multiplied by n. And x is larger or equal than 1 over 2. So therefore, when you consider like all coefficients, you take the coefficients which are from the right-hand side of the middle of the interval. Therefore, the maximal coefficient is here the coefficient with the minimal number k here that is considered. So here. Therefore, let's note that taking L that is equal to xn. So it is the integer part of the number x multiplied by n. Actually, so that you get that maximum of Cnk, and then k is larger or equal than xn. Actually, can be attained in. Oops, I apologize. It's not C. It is nk. Can be so here and L. And okay, then we can control maximum by only one binomial coefficient. And you see that in binomial coefficients, we have to work with factorials. Therefore, we need some kind of asymptotic of factorials, or know how fast they goes to infinity. And for that, we have a ceiling formula. In analysis, let me recall that formula, or recall that here formula, which says that factorial is approximately like n to the power n, e to the power minus n, and then square root 2 pi n, plus up to some error, that is here 1 over n. Of course, as n goes to infinity. So therefore, let's come back to our estimates and or our computations, and let's consider what is the limit 1 over n of logarithm of maximum nk k larger or equal than nx as n goes to infinity. As we said, that is a limit n goes to infinity 1 over n, and then this maximum v just replaced by that one concrete coefficient like is nl, where l is defined it was defined I do not see, I see l is defined here. And then let's continue using the precise expression for binomial coefficient. It is limit n goes to infinity 1 over n, and then you have logarithm n factorial, l factorial, n minus l factorial. And then by the properties of logarithms, you see that that equality here can be written like limit n goes to infinity 1 over n logarithm of n factorial minus logarithm of l factorial minus logarithm of n minus l factorial. And then we use the steering formula. So actually into this logarithm, we may put this expression here. And then you will have a logarithm of that product. But logarithm of that product, you will have the sum of logarithms. And then you will see the logarithm of that will gives you n logarithm n by the properties of logarithms. Logarithm of that will gives you minus n. And logarithm of that, okay, it will be like this term, but later you see that you divide it by 1 over n. So for this term will disappear. Let me just write what you will get at the end. You get limit n goes to infinity. And it is logarithm n minus 1 minus, then for the second, l divided by n, logarithm l. Then you have minus n minus l divided by n, logarithm n minus l, plus n minus l divided by n. And then you just want to combine that terms together. For that, we will write the logarithm here as a sum of two terms. One term, it is L divided by N, and then you have logarithm N. Then you will have also plus N minus L divided by N logarithm N. You see that when you sum them together, you will get exactly this term. So actually that here, it is that. Then you have minus L divided by N logarithm L minus N minus L divided by N logarithm N minus L. And also you have it seems that when I wrote that formula here, also I forgot to write also the term like the last one. You have minus L over, you have plus L over N. So therefore, let me, so it's a little bit sloppy. Let me do this like that. I will move plus L divided by N. And then combining this term together with this term, you will see that you have n divided by n. It is 1. And you have also 1 here. So it gives you 0. So then it is the reason why I don't see this term, that term, and that term here. And now writing or combining this term together with that term, you will see that it is L divided by N logarithm L divided by N, but with minus. So it is minus Ln logarithm L divided by N. Then you have minus N minus L n logarithm n minus L divided by n. And now let's recall that L, it is equal to the integer part of xn. Therefore, when you divide that by n, it is here divided by n. And of course, this goes to x. The reason is that the integer part of this you can estimate from above like xn plus 1 divided by n, and from below like or maybe here without 1, and here you can estimate like that. And you see that when you divide by n, so this term and that terms, they both goes to x, therefore also the term between must go to x. So then using the continuity of logarithm, you see that this term goes to x, this term goes to x, and this term therefore will goes to 1 minus x, because you can write the difference like 1 minus L over n, and this also goes to 1 minus x. Then we can continue, or we can write that that maximum here is written minus x logarithm n. Okay, and then let's come back to the estimate which we had before, or let's come back to the probability. N goes to infinity, 1 over n logarithm of the probability that 1 over n Sn larger or equal than x. Oh, what it is here? You remember that we estimated this probability, the probability inside the logarithm. N plus 1 divided by 2 n, and then you have maximum nl. And it is equal to lim n goes to infinity 1 over n logarithm. And here also again by properties of logarithms you will have n plus 1, then you have minus 1 over n logarithm 2n, then you have plus 1 over n logarithm maximum. Here, let's be more careful. Oh, I'm sorry. So it should be here x, x larger or equal than that is k, here xn, and then this maximum, so it should be maximum. And k. After that, you see that that the limit that this term goes to 0. The same reason that logarithm is slower as the linear function. This term, it is equal to logarithm 2, because you may move that n outside and you have n divided by n. And this term we already computed, and you see that its limit is equal to minus x logarithm x minus 1 minus x logarithm 1 minus x. Therefore, that the result here, it is logarithm 2 minus x logarithm x minus 1 minus x logarithm 1 minus x. And again, this computation, you remember, were done for x larger or equal than 1 over 2 and smaller than 1. And then you also, now, like as a second step, you need to estimate this from below. But when you write the estimate from below, you will have the same expression, but without this term. Therefore, you then don't have only this term in your computation. Then it's trivial. Then from below, you can estimate by the same term. That implies that this limit exists, and it's equal to precisely this number. Let me summarize that. We have obtained that limit n goes to infinity 1 over n logarithm the probability of 1 over n Sn larger or equal than x is equal to minus logarithm 2 minus x logarithm x and minus 1 minus x logarithm 1 minus for x from 1 over 2. And now let's take the function. Take the function I of x of the following form. It is logarithm 2 plus x logarithm x plus 1 minus x logarithm 1 minus x for x from 0, 1. X from 0, 1. And then plus infinity. If otherwise, let's sketch the graph of this function. And when you do that, for instance, with computer or with some analysis methods, you can see that the graph, it will looks as follows. Here is 1 over 2. Here is the interval 1. Then you will have, so this write like that, but actually this line, it is plus infinity. So here it is actually plus infinity here. Here also it is plus infinity. The function is equal to plus infinity. And here it is a function which looks like parabola, but of course it is not. It is symmetric with respect to the line 1 over 2, x is equal to 1 over 2. And here it is logarithm, it is ln2. Why it is ln2? Because you see that when you consider that formula, you see when x goes, for instance, to 0, this terms goes to 0, that terms goes to also to 0, and you get logarithm 2. And the same for the right-hand side. And of course, we understand this equality also for x including 0 and 1 as a limit. Okay, you have that function, and we showed that this limit, it is minus that function at point x in the case when x is on this interval. And then using the symmetricity of Bernoulli distributed random variables, we can also easily get the result for this part. Let me just make that comment. It is a remark. Um, 1.2 in the script, which says that using the symmetry, we have that limit n goes to infinity 1 over n logarithm the probability 1 over n Sn less or equal than x is equal to minus I of x for x larger or equal than 1 over 2. And that also includes the case also smaller than the 0, because you see that here we write not precisely this, that expression, that expression, but also including, including also plus infinity. So therefore, it is true for every x larger or equal than 1 over 2. And the reason, or how we use here that's the symmetricity is the following. Indeed, just taking the limit and goes to infinity, 1 over n logarithm the probability 1 over n as n less or equal than x. You can do, you need to reduce that to the case when you have larger or equal than x. Therefore, you can consider, you can write this as the limit n goes to infinity, 1 over n, logarithm, the probability, and then write minus 1 over n Sn is larger or equal than minus x. Here I did nothing, just multiply by minus 1. Then I write here minus 1 in the left-hand side and in the right-hand side. But here I will write that as n divided by n. And then I continue. This is 1 over n logarithm, the probability. And here you have, in the numerator, you have n minus Sn. Or it is the same as you have like as 1 minus x1 plus 1 minus x2 plus and so on to 1 minus xn divided by n, larger or equal than 1 minus x. And you see that the random variables which are here, they have the same distribution as the random variables xi. Therefore, you have, and by the way, these constants now here is larger or equal than 1 over 2. So therefore, you will obtain by the previous result that it is minus I of 1 minus x. And now when you will go to this function, you see that it is symmetric. Therefore, it is minus I of x. For, as I said, for x less or equal than 1 over 2. Okay, now we came to the following result, that for the case of tossing of coins or for independent Bernoulli distributed random variables, and we consider it the case when the parameter p is equal to 1 over 2, but of course you can do everything similarly for any parameter p. And then we came to the concrete part, and we investigated that the probability goes exponentially faster, but the exponents here is given by this function I that has a specific form. Now, let me summarize this as the following theorem. 1.1. And we have let C1, C2, I just write C because I just want to be like more general, just want to change a little bit notations. Be independent, Bernoulli distributed, random variables with parameter p that is from 0, 1. So that is p of ck is equal to 1 is equal to p, and p ck is equal to 0. It is 1 minus p for every k. Let also Sn is equal to sum as before. Then we have that that for every x larger or equal than p, you have that limit n goes to infinity, 1 over n logarithm the probability that 1 over n x Sn larger or equal than x is equal to minus I of x, where I of x is equal to, and now of course the function has more general form. And by the way, this constant 2, I didn't set that, but using the properties of logarithms, you can move this constant 2 inside that logarithms here. Therefore, you will have the function x logarithm x divided by p plus 1 minus x logarithm 1 minus x divided by 1 minus p. And it is for the case x is from 0, 1, and plus infinity otherwise. Once again, we didn't prove that theorem in this generality, and you can consider that as an exercise. Size 1.4 in script proof rule theorem 1.1. Let me also tell you a few words. Again, I want to come back, first of all, again, just to say a few words why this result can be useful for us, like just from the first look. And here I want to formulate this as an exercise also for you. Exercise. It is 1 over 1.5. Then using that theorem 1.1 for p is equal to 1 over 2 show that the sum n goes from 1 to infinity, the probability that Sn divided by n minus 1 over 2 larger or equal than epsilon converges. Oh, I'm sorry, convergence. And probably even now it is not complicated to believe that this result is true, because you see that this type of probability should go to 0 exponentially fast, and the series with exponents with e to the power like minus something multiplied by n, it converges. You know that from the analysis. So you have the convergence of this series for free, and after that you can use the Borel-Cantelli lemma to conclude that Sn goes to n goes to 1 over 2 almost surely. You can get this type of convergence almost surely, just when you are able to control the tails of some probabilities. And also, when you go, for instance, I would recommend you the book, very nice book of Ellis, Entropy, Large Deviations, and Statistical Mechanics. You write that book. Ellis is Entropy, Large Deviations, and Statistical Mechanics. I showed you two models, one model or two examples. One example, it was a family of independent normal distributed random variables. And there you saw that the rate of convergence is described by the function which is equal to x squared divided by 2. And we considered another example, Bernoulli distributed random variables. And you saw that this result is completely different. But okay, but what about the exponential distribution? What about that? What's about I do not know, geometric distributions and so on, or any other distribution? Should we do for every case a specific computations, or maybe there is some general result which would allow us to cover, say, all or almost all distributions and give an answer what the rate of convergence is when you consider the sum of independent, identically distributed random variables. And it is exactly what we are going to do next time. Next time, we will discuss this result that is called Kramer's theorem. So therefore, I will try to explain you the result, and also we will start the proof of the Kramer's theorem. And after that, we will go to the general definition of large deviation principle. It is everything for today, and thank you for your attention.